So these are your standard functions that you should have learned at least the first 7 or so. Maybe you haven't looked at exponential, logarithmic, or reciprocal functions. But in Algebra 2, constant functions, that's just y equals a number. That's just a horizontal line. Linear functions, that's y equals mx plus b. Your standard linear function is just y equals x. Absolute value function, that's y equals the absolute value of x. Quadratics, you should have done those a lot in Algebra 2. Y equals x squared. Cubic functions, x cubed. Root functions, y equals the square root of x. You probably, starting here, may not have done this in Algebra 2. These you may not have done, but this first set should look familiar to you. And so these are called parent functions, meaning there's no movement from the origin, all right? They're just straight y equals x squared, y equals x cubed. There's no plus or minus, there's no coefficients. It's called a parent function. And so in this section, we talk about transformation of parent functions. We're just going to do straight transformations. And then tomorrow, we're actually going to get into quadratics and moving those around. So we're going to do a lot with this guy right here. So these are parent functions. And what you'll find is you can move parent functions vertically. You can move them horizontally. You can reflect them across the y or across the x-axis. And so there's a lot of things that can happen to shift these around the graph. And usually when you do transformations, you are sketching, right? So when you're sketching a graph, you need to recognize which is the parent function and know that particular little guy. And then you're just sketching basically what it would look like and where it would be. It's not an exact, it's not like you're using a graphing calculator and you're getting this exact picture. You're just kind of sketching it and seeing where it's going to land on the graph. And so the first two things we're going to look at are vertical translations and horizontal translations, okay? Vertical moves it up and down. Horizontal moves it left and right. Now what you'll find is this represents the parent function. And if you take that parent function and then outside of the function add or subtract something, it's going to move that function up or down. The example that they've given us here is this dashed line represents f of x equals the absolute value of x. That is my standard parent function. So if I just gave you absolute value of x, you're going to get this perfect v that has a 1 slope and a -1 slope on either side. But then if I were to take that same function and add 2, all it does is it shifts this guy up 2. You'll notice it didn't move it anywhere else on the graph, it just moved it up. If I were to do the same thing here, you will see that down here, it's -3. And so we've taken this and we've gone 1, 2, 3 down. Same exact function, we've just translated it, moved it down. And so you probably did translations in maybe geometry, with maybe geometric figures, sliding them around the coordinate plane. This is conceptually the same thing. We're just sliding it up and down. Horizontal, you're also adding and subtracting, but you're doing so within the confines of the function itself, all right? So here, you'll notice that the plus or the -3 was outside of the absolute value. That tells you this is a vertical, up and down. But over here, my parent function that we're dealing with is just x cubed, right? This is my x cubed parent function right here. And now we have a +3 inside the cube, and we have a -2 inside the cube. Now, the thing about horizontal translations is they do the opposite of what you think your brain was telling you to do, because the original piece up here is minus, okay? So if I have a +3, I'm actually saying minus -3. So you're actually moving opposite of the way you would think. You would think a +3 would move you to the right, because that's what our brain wants it to do. But because my original was minus, you're actually subtracting a -3 here. So it moves you to the left. So when it is inside the function like this, it moves the opposite of the way you think it's going to move. A +3 inside the function moves the whole thing to the left, 3 units. A -2 inside the function moves the whole thing to the right, 2 units. All right? Any questions about vertical and horizontal translation? So when you are shifting a parent function, you need to first figure out, what function do I have? Do I visually know what that should look like? Yes, that's a parabola. And then how has it moved? Well, inside, left, and right. and then outside, up and down. And so I've shifted it in the direction and the number of times that it told me to shift it, and then I sketch the graph. All right, so reflections can move you different ways. So they can reflect you either across the x-axis or across the y-axis. And you can think of reflections just like you did in geometry. Reflections take a figure and they, just like a mirror image would do, would flip it across that figure. You have a line of symmetry that flips it all the way across. And so if you have a negative on the outside of the function, you'll notice this negative is in front of the function. That is going to be a reflection across the x-axis. So remember, my x-axis is my horizontal axis, which means it's going to flip up and down. All right, so when I reflect across my x-axis, I'm going to flip up and down. When I have the negative on the inside of the function, I am going to flip across the y-axis. And so I am going to take my original function here and mirror it across the y-axis. And so those are reflections. So if I look at these particular ones, describe the transformations of the graph, all right? So for this one, my original function they gave me was x to the fourth. So I have x to the fourth here, right? They have reflected it. So we went from this direction, and obviously we're now going down, which for this it's kind of hard to see because obviously we reflected it the other way, it wouldn't move. So we reflected it down, which means it's across the x-axis. So I know that I'm going to have this x to the fourth, and I am going to have a negative on the outside. It's not going to be inside. And then once I reflected it down, so if I had reflected it down here, I then moved it, and I moved it up 3 units after I reflected it. And so that would be what that would look like. I reflected it and I moved it up after I reflected it. Okay? Let's look at the next one. They tell me my original graph here is 1 over x. So I have flipped this guy down here and I have flipped that guy up there. So obviously I've negated it. But then I did a horizontal, right? I did a left-right movement here, not an up-down. So now within the function, I need to move it. So within this x, I need to do a plus or minus. I moved it to the right. Remember, it's opposite when it's on the inside. I moved it to the right from here over to here. This is my new line. So I moved it 2 places to the right. That function is going to look like that. All right, so you have 2 things you need to be able to do. One, if I give you a function, you need to be able to sketch it based on the parent function and how it moved. Or if I give you the function itself, you need to give me the definition of the function or the rule for the function based on the movement that you see on the graph. If I look at this first graph here, the square root of x, this is my original graph. What happens when you multiply it on the outside here by 2 is I get this pull upwards. Okay, so you can think of every y value after I calculate it here is then going to be multiplied by 2. And so we get this stretch that happens as we pull that out, right? We pull that out. So I have my original, and then I have this stretch that happens when I pull it out. If I look at what happens with the 1/2, it actually pushes it down. So you have a pull up or a push down on the graph. And so it causes a stretch or a shrink depending on what you have. And so we have a pull this way or pull that way, right? If we look at this one, and I think they have their markers off, which looks weird. If we put it inside, and I think what's happened is they've written this wrong, so we're going to fix this. This should actually be written like this. We'll fix it for them. Inside is going to be a horizontal. Remember, vertical is on the outside of the function. 2 is on the outside. 1/2 is on the outside. Horizontal is always on the inside of the function. So on the inside of the function, instead of pulling it up or down, it actually pulls it left or right. They look very similar, but think about what's happening. Every y value here is being multiplied by 2, right? Every y value here is being multiplied by the square root of 2. So it affects the function depending on what type of function you have, right? If it's inside, it's going to happen before anything else happens. So let's say this was a square or a cube. If I put it on the outside, it's actually going to affect it less because I'm not cubing or squaring the number. Here, it affected less inside because it was a square root of a number. So it kind of depends on the function as to how much it's going to affect it. But if it's on the outside, it's going to pull it either up or down. If it's on the inside, it's going to pull it left or right. And that's kind of the same concept as vertical movement and horizontal movement, right? On the outside of the function, it moved it up or down. On the inside of the function, it moved it left or right. And that's the same thing that's happening here. It's pulling it up and pulling it down. Outside, it's pulling it to the left or pulling it to the right on the inside. And it's stretching that function. And again, you're sketching. So once you figure out, okay, I know what my parent function is, I know it's going to be a little bit skewed. If it is a whole number that's multiplying it, it's going to pull it either up or left. If it is a fraction, it's either going to pull it down or right. Okay? So a whole number is going to pull it up or pull it left. A fraction is going to pull it down or pull it right. That's what's going to happen to these depending on if it's inside or outside. All right? So for this one, we have a parent function of x squared. Remember my x squared function, they give us the dashed line here. That is my straight parabola. Now, two things have happened here. This negative, what is this negative going to do to my parabola? It's going to reflect it, right? So instead of going up, it's going to be going down. Everybody see that? I'm also multiplying by a 3, all right? A 3. And so if you look, what they did is they stretched it first and then they reflected it. So they stretched it by that 3, which is on the outside of the function. So it pulled it up, right? It pulled it up. So it made it skinnier. So you can think of if you took this parabola and you were to pull up on it, it would make that parabola skinnier, right? Think of it almost as a rubber band. Then once they pulled up on it and made it skinnier, they reflected it down because of the negative. Look at the difference between that and this one. All right, they wrote this x over 3. Another way to write that is 1/3 x squared. So 1/3 x squared is going to pull it, and it's going to pull it away versus towards the origin. So for this one, I'm pulling away from the origin versus towards the origin. So this 1/3 actually flattened it because it was inside and it pulled this way versus pushing this way. And so you can see this guy made it a lot wider when they multiplied by 1/3 versus a 3 on the outside. All right. Now, if they had a 3 on the inside here, it would have pulled it this direction really tight. So let's look at this one together. So the first thing I want to look at is, what is the parent function? What is the parent function? All right, so I'm going to look at this right here, and this is going to tell me my parent function is y equals x squared. Y equals x squared is a basic parabola, right? It's a basic parabola. So I've determined my parent function. The next thing I'm going to look at when it's like this is that I'm flipping it and I'm stretching it. That -2 tells me it's no longer going to point up, it's going to point down. And because it's a number, absolute value bigger than 1, it's going to pull it, right? It's going to stretch that thing. And so it's going to pull it this way, which means it's going to get skinnier. Think of a rubber band, right? If you had a parabola-shaped rubber band and you pulled on it, it would get skinnier. And so that's what that 2 is going to do. The 2 is going to make it skinnier. The negative is going to flip it upside down. So that's the next movement I did. And then I'm going to say, well, I have a -3 on the inside. That moves it right 3. I have a +4 on the outside. That moves it up 4. So I go to my vertex right here, the green one, this guy right here. And I am going to take that vertex and walk it according to this movement. So I'm going to walk that vertex to the right 3 and up 4. And that's where I'm going to put this final version of that movement. Okay, so I had to do the parent function, whether it reflected or stretched, and then horizontal and vertical movement. So we've been given rules, and by rule I just mean f of x equals x squared plus 2. That's a rule, okay? And they gave us the rule and said, I want you to draw that rule on a graph. I want you to give me a picture of what this rule looks like. Now they're doing the exact opposite. They have given us a function on a graph, and they want us to describe the rules for the functions. So they've actually given us 2 different functions. They've shown us the parent function, which I would not give you, right? So I'm not going to give you this guy right here. You're going to have to know that based on the shape of it. But based on the shape of this is a quadratic f of x equals x squared. That's my parent function. They want me to write a rule for g, and they want me to write a rule for h. Now, I will say, I'm not going to be this specific. There is a way to figure out exactly what the stretch is, but right now I'm not going to make you be that specific. I will show you how they did it, though, so that you can get an idea of how this is done. So let's start with our g function, g of x, all right? The easy part for g is that it moved, right? So for g of x, we know that it moved which direction from the original, left or right? It moved to the right. That's on the inside. So if my parent function is x squared, on the inside, I want to go right 1, 2, 3 places. And remember, it's the opposite of what you think. So I'm not going to say +3 inside. I'm going to say -3. So that much I know, right? Now, it's also pretty obvious that he got skinnier, right? So we know that he stretched. And because he got skinnier and not fatter, he actually stretched by a whole number. And we know it's positive because he didn't flip upside down, right? So we know there's a positive number in front of this particular graph. Now, the way we know exactly what number it is, my slope, so to speak, so if I go from 0, 0 to my first crosshairs, it's a 1, right? Up 1, over 1. Everybody see that? But now if I look at the next one, if I go from here to my next crosshairs, it is 2, right? And that's how you know how much it stretched. It stretched by 2. And so this guy is going to look like that. All right? Let's look at the next one, h of x. Again, we know my parent function. We know he also shifted, right? Specifically, he shifted down, right? He also reflected. So we have a lot of stuff going on here. But because he shifted down, it's on the outside. So I know I'm going to have an x squared, and I went down by 1 unit. So I'm going to subtract 1 from that, right? In front of the x squared, I know two things. He got squished, which means I'm going to have a fraction, and he flipped upside down, which technically is going to be a negative fraction, right? And so again, remember this movement here was up 1 over 1. If I do this same concept, it's going to be a little bit harder to see because this still looks like it's going to be a 1 movement, doesn't it? Up 2 over 2. It's actually technically a 1/2 movement, which doesn't look like it. So this is where I said I'm not going to make you do it exactly for me. As long as you can say, okay, I know it's skewed. It's skewed. It went from up to 1 and it went up 2. So we're going to say 1/2. It actually is a 1/2. But what I'm looking for is, do you know it was negative and do you know it was a fraction? So even if you don't know exactly what the fraction is yet, and we'll get to the point where you do, it's okay. You can estimate it, right? You can see this is the origin. It went 3 places to the left, which is a +3 on the inside. And they gave you the parent function +3 on the inside. This is also stretched, and if you're not extremely familiar with this parent function, this also does a 1-to-1 movement, and you can see it's a 1 to 1/2 movement. So this is where that 1/2 came from. So you may not be as familiar with this guy, and you may not have recognized that he stretched, but he stretched as well. He got skinnier as well, but he got skinnier with movement pulled this way. So he's a little bit different than the other one.